The decoding model, uncovering the mystery of color vision. Young and Helmholtz's theory of three pigments. Young and Helmholtz's three-pigment theory believes that the human eye contains three color-sensitive cells, which are sensitive to red, green, and blue light respectively. Different combinations of the three signals lead to different color perceptions. Hering's opponent process theory. To explain the negative afterimage phenomenon, Hering proposed the opponent process theory, which believed that the human eye transmits red-green and blue-yellow color signals to the brain. Popular zone model unifying the two theories. The zone model explains that color information exists in the form of three pigments in the visual cone zone, and in the form of opponent colors as the outputs of ganglion cells. There are two forms of the zone model. The main difference lies in how the yellow signal Y is generated. The second difference is that in model B, G, and R are replaced with S, M, L, which means short, medium, and long wavelengths. Problem 1 with the zone model. Red and green are not complementary colors, such as red and green in zone model A. There should be three pairs of complementary colors, red and cyan, green and magenta, blue and yellow. Problem 2 with the zone model. Problem: color transformation between physical system RGB and psychological system HSB, hue, saturation, and brightness. The above-mentioned zone model cannot provide the conversion between trichrome signal and psychological color signal. At present, the practical transformation is put forward by Alvy Ray Smith and has nothing to do with the popular zone model. Smith's method is compatible with the decoding model. Problem 3 with the zone model. It is difficult for the zone model to get the number of unique colors. A unique color only stimulates one color-sensing cell in the brain. However, according to the zone model, R plus G equals yellow Y, so the unique color cannot be unique. Therefore, what we need is logical operation rather than arithmetic operation. From the 3 to 8 decoder to human color vision mechanism. The 3 to 8 decoder commonly used in digital circuits is used for address selection. It can output a unique signal. For example, for the color vector 0, 1, 1, only yellow is not 0. The color mechanism of the human eye can be understood as a fuzzy 3-8 is equal to -5 decoder, which can make the signals of three vertices of a sector not be 0. The 3 to 8 decoding model of color vision mechanism. Using the analog logic operation, the unique color problem can be solved, and it can better unify Young-Helmholtz's theory of three pigments and Hering's theory of complementary colors. In the decoding model, first the horizontal cell produces M's signal, and then R, G, B are subtracted by M to get three pairs of unique colors, namely red cyan, green magenta, and blue yellow. A realized physical model. Cone cells receive color information to get R, G, and B. Ganglion cells output three pairs of complementary colors. Only three adjacent LEDs will light up, reflecting the proportion of two unique colors and white. Illustrating the evolution of color vision. With the decoding model, we can explain the evolution of color vision by splitting the color sensitivity curves of cone cells. We can imagine that the human eye initially had only one sensitive cell, only seeing in black and white. Then, sensitive cells split into two kinds, and the human eye could also see blue and yellow. Later, the two kinds of sensitivity curves split into three kinds, and so the human eye can now also see four other unique colors: red and cyan, green and magenta. Illustrating various kinds of color blindness. Color blindness is not because one can't see a certain color, but because one can't distinguish some different colors. Red-green color blindness is because the G curve and the R curve are not separated. Blue-yellow blindness is because the B curve and G curve are not separated. Achromatopsia is because the three sensitive curves are not split. Color transformation between the physical system RGB and the psychological system HSB. The computer industry uses the conversion method of computer expert Alvy Ray Smith, which is completely compatible with the decoding model. Using logical operation at the three vertices of a fan in the graph, we can decompose a color vector, B, G, R, into a linear combination of two unique colors and white. Using the three components, we can get the hue, saturation, and brightness. CIE also adopted this decomposition. Correspondence between Chengwang Liu and Mr. Smith. Around 1990, Liu Chengwang told Smith, "Your color conversion algorithm is completely compatible with my decoding model." In 2016, the two met on ResearchGate.net and were happy to congratulate each other. References. You are welcome to communicate on the author's homepage. The link survivor99.com/lcg/English.